Good morning. Let me start by thanking Jacques and his team for the organization of this workshop. It's already certain to be useful and interesting, and I'm very appreciative of everything you've done to get us here. So you see this as a review paper. Now, I don't know whether it's useful to use a laser. So we're going to review the power and the energy densities that... Thank you. That's a problem I have. For French people? Well, for everybody. Thank you. I appreciate it. So I'm reviewing the power and energy densities that have been achieved in some LENR experiments and will suggest their promising implications. Okay, so let's see. Does this work? Maybe not. You have it on next. Yeah, I tried. Next. I tried. Did it work?
Engineering board.
Yeah, thanks very much. So excuse me. If I start too fast again, remind me, please. The outline of the presentation will be to remind you of some of the features and implications of LENR and the associated advantages of high energy densities. I'll tell you again what you may already remember about Ragone diagrams. Maybe not everybody remembers them. And the core of the talk is shown in red there. We'll talk about Ragone diagrams for LENR and some important experimental results, and then I'll wind up with the single view graphs that shows a summary. So we know from literally thousands of LENR experiments over a third of a century in a dozen or more countries, a great deal about the subject. And we focus on what we don't know, theoretical understanding, materials control, all kinds of things, but we really already know a great deal, and it's summarized here. We know it's possible to get high energy gains, which indicate potentially very low cost energy. I'll jump over that. Little radiation during operation is safe, negligible radioactive waste, it's environmental friendly, no greenhouse gases. Yeah, thank you. Yeah, again, it may be possible to make generators that are available all of the time. They're going to be small because of the high energy densities, and they should not cost too much per unit. They should be affordable, okay? So that's the promise. And it's worth celebrating this set of characteristics. I mean, if you look at a comparable list for hot fusion or fission, you'll find a very, very different situation. We have a lot going for us already. And you have to note that many scientific, engineering, and other challenges have to be overcome. I'll have a list of a few of those at the end. But we have very nice prospects. So returning to the high power and energy densities, we have the prospect of widely distributed nuclear power sources, which would be a historic development. You know, it could be viewed as in the same class as the development of silicon-based microelectronics. I mean, it could really, really change the world. So we'll see. Now, the advantages of such high densities are listed here, having small energy generators in homes and other small buildings. The consumers would control the production as well as their use of energy from a nuclear power source, not a large facility many, many miles away. Lower installation and maintenance costs, no need for the electrical grid. It would be in your home. And of course, the grid is lossy, so that they avoid the losses there. And it would be possible to have power in remote locations far away from the grid. It might even be possible to have mobile power sources that would enable to replace diesel generators, which of course are smelly and noisy and so forth. Small generators that could be brought quickly to emergency situations and for things like concerts and other things. So the reason I'm offering you this review paper is because I think the high power and energy densities that are likely to be available from commercial LENR generators are going to be incredibly important. Now, to remind you what a Rogaine diagram is, you have energy density is watt hours per kilogram on the horizontal scale, the logarithmic scale, and power density, watts per kilogram on a vertical scale. And this is a well-known diagram. Here's a lead acid battery, a petrol engine over here. So this sets the stage, if you will. And I draw a diagram around those things and then shrink that into the corner of this diagram, expanded so it's possible to include the LENR experiments that have been done in the past. This diagram is a mixture of old and new. Oh, I'm sorry. Okay, there. The data from energetics technology is new. The other points were calculated many years ago. We return to them, and I will update this graph late in the presentation. The key point is the power densities that are available from LENR are dramatically higher than those available from ordinary energy storage and generation sources. And it's the same is true of the energy density because of the megavolt to EV ratio that we have in our field. Okay, so, pardon me. What I'll do in the next few view graphs is walk through these 4 experiments. Italian experiment, an experiment done in Israel, an experiment done in Rossi's lab, and then an experiment done by Schwartz. You see the different years here and the different types of experiments. So starting with the Preparata experiment. Yeah, thanks very much. I have a drinking problem. Thanks, Lon. The Preparata experiment reported in 1996 at a 2.5 meter long palladium wire, 1/4 of a millimeter in diameter, in a very large, what's that say, 28 centimeter size cell. And the important thing here is that he and his colleagues achieved power densities, watts per cubic centimeter of the palladium, that were comparable to the power densities available from fission fuel rods in a wet experiment, okay? A very noteworthy experiment. The data itself is shown in the next graphic. It's a graph of time horizontally versus the power. Input power is on the order of 80 watts. The output is about double that. It lasted at high levels for about a half an hour, roughly. So here we have an experiment that is extremely noteworthy and old already. So Emma Morano and I are expecting to do that in the rest of this year, working in our lab at George Washington University. So that's one. Turning to the second, the electrochemical experiment reported by Dardick and his colleagues in energetics technology. This is a photograph of the experiment. The key thing, the data at the bottom here is 62 watts per gram of palladium, 750 watts per cubic centimeter. Excuse me, sorry. And you can see that the similar values for a fission reactor are shown here. So these are very, very substantial compared to what's available in a fission reactor. This is the actual data. Many of you have seen this before. It's a 17-hour duration in which the input was on the order of a watt, and the output was shown here at a very, very high energy gain. Okay. Remarkable experiment. It had a second phase, which is shown here. I'm going to skip over that in the interest of time. The point is that they achieved very, very high gains and associated power and energy densities. Okay, turning to the Rossi experiment, this is a cylinder that's roughly this big in diameter, about that long, and was measured by Levy and his colleagues. They produced a report that's indicated. They measured the output using thermal emission, infrared camera. They got values here that are plotted on the graph that's coming up. This is data from Schwartz. He produced a Ragone diagram. He had here the lead acid battery. He had the nanor relative to that. So we put all this together in a revised diagram. We have the same axes shown here, log energy density horizontally, log power density vertically. Here are the conventional sources, and here are the LENR related sources. The values for the Preparati experiment, the ECAT and the DANOR have changed because of a reanalysis, but the fundamental point is that there are many orders of magnitude between what we know already and the prospects of LENR, okay? So this is essentially the take-home graphic. Now, you can object to this, I would if I were you, got so many orders of magnitude uncertainty, both, especially in the horizontal axis, but even the vertical axis. But the point is that what has been done in a few experiments in our field so far, 2 of them wet experiments, the Preparati experiment and the energetics experiment. This is a dry experiment, a hot gas experiment. This is a small device the size of a pencil that produced very, very strong results. So we have multiple kinds of experiments in different hands at different times with different diagnostics indicating that we can achieve very high power and energy densities in this field. So to wrap up, this is the summary of the challenges and the potentials of these high power excuse me, and energy densities. The problems are we need materials and procedures to give the high gains in order to realize the high power and energy densities. We have to scale the power up to the multi-kilowatt level. If you, I'm asking you to, okay, we talked about this. Jacques shaking his head. But imagine it. Microphone, please. Imagine a plot that says 1 watt, 10 watts, kilowatt, 10 kilowatts, and so forth. Okay, the applicability of LENR shoots up when you get to the kilowatt level because you can power individual homes. Okay, you need a kilowatt or a multi-kilowatt. So from my perspective, the scaling to the kilowatt level is interesting. Jacques disagrees. He's going to tell us why. And we need reliability for adequately long times. I am very concerned about the durability of LENR materials. We need particular structures. We need particular chemistry and so forth. What happens when you heat a material? Diffusion. It's relentless. You can't avoid it. So whether or not we can produce materials that will last long enough to give us the high performance that we need in order to realize the advantages of these high power and energy densities is a very open question. And another thing that's not discussed much is the ability to control the output power. You know, it can be done, but the time constant involved, it's not going to be like a ordinary petrol engine where you can step on the gas and it takes off quickly. It's going to take time because of thermal inertia to respond both up and down. Now, if those problems are solved, we have the possibility of distributed nuclear power and energy sources that we expect will lead to a new clean energy industry, which is why Steve Katinsky and I formed LENR many years ago. So I thank Emma Morano for help with this presentation, and I thank you for your attention.
Okay, thank you very much, Dave. I could make hours of comments about that, you know, because we share such presentations before. And in terms of energy densities, to run mobile equipment, you know, and to have long working possibility to run such reactors for a long time is quite contradictory. Because if you have a high temperature, if you have a high energy density, you need a high temperature. And if you have a high temperature, you may kill your system too early. So there is an optimum to be found. So there is some work ahead of us. Huh? Any question?
Yeah. Yes, if I. So hello, thank you for the presentation. I wanted. Not working? Yeah. So My question is very quick. So to bridge the gap between fundamental research and the kilowatt power level, I mean, it's a big jump. So you and your group, are you already working on bridging this gap? For example, talking with potential commercial users and together with the researchers too?
Yeah, so the field, of course, has two parts, the science and the commercialization. We're working on the science side, but very interested in the commercialization side. We'd like to get into that, but we're not in it yet.
Because maybe one does not need to jump to the kilowatt level immediately.
Oh, no. So, I agree, but that's the sweet spot from my perspective.
Thank you.
But some labs in the world are already on this path, you know, including in this room. In this room. Find the guys. Okay?
So, thank you very much.
Thank you very much.